This is a measurement of a single channel fiber Bragg grating using the virtual reference analyzer. We've connected to the fiber Bragg grating, which has two FC-APC ports on both sides of the grating. So those are the connectors. And we've connected to this fiber Bragg grating through using a hybrid FC-PC to FC-APC connector. So the FC-APC connector is connected at the DUT port, and the FC-PC connector is connected through a fiber connector to the FC-APC port on the fiber Bragg grating. Side A of the fiber Bragg grating, and this fiber Bragg grating is a negative, has negative dispersion. It's a dispersion compensating grating. Okay. Now what we've done, the settings on the amplifier inside the VRA is set to 0 dB. So the gain on the sensor is at 0 dB, and this is actually crucial for measuring DWDM devices. Okay, so we have 0 dB gain on our sensor, and we have an output power from our tunable laser at 1 dBm. Okay, and we're checking our TLS port. We're going to refresh, and we're connected. Our TLS port is at GPIB 20. So we click on that, and we're using an 81600 B series tunable laser in an Agilent 8164B mainframe. Okay, we're going to use 50 points for now. Our compression factor is 1. We're not using compression in this experiment. And since the FBG is a bulk reflective element, we click here. Okay, it's a bulk reflector. So let's scan. So the laser is going to scan from 1530 to 1570. I'm not sure if you could hear the click from the laser, but it's just started. And should be completed now. And here are the results. So we have the full scan, the raw scan pattern here. And what we're going to do is we're going to isolate the grating reflection spectrum. Now this looks like a Fabry-Perot. It actually has the outline of the reflection spectrum of the grating, right? But it's got this high frequency interference pattern, and that comes from the Fabry-Perot cavity that's formed between the front facet FC-PC reflector and the fiber Bragg grating. So there's a cavity formed in between there. Okay, now the power spectrum, this peak of the power spectrum is, it tells us the group delay of the cavity, the group delay difference between the two reflections in our real cavity. Because what we're going to do is we're going to create a virtual cavity, a free space, so it's going to have no dispersion, and it's going to have the same group delay as the real cavity at a particular wavelength, and that's denoted by this. See this big peak here? The center of this peak is where the group delay is equal. So it's equal at one wavelength. Okay, so and it's going to be equal at different wavelengths, because as we change the group delay in our virtual cavity, it's going to balance the real cavity at another wavelength, and that's because of dispersion. Okay, it's going to be equal at a specific wavelength. So what we can do, I can show you a little bit about. So we have this sensitivity basically. When we click on the button, it's the amount of change, the amount that we move our interference pattern to the right or to the left. Now, because this is a negative dispersion, when I click to the right, the center moves to the left. Okay, that's what happens with negative dispersion. Okay, now I have to be very clear when we're making this type of measurement. If the gain on the inside of the VRA, the gain of the sensor on the inside of the VRA is not set to 0, then basically we're going to have phase jumps in between here, because we're going to have a lower output power So we want to make sure that the gain on the inside of the sensor inside the VRA is set to 0, and the output power is at least 1 dBm from the laser. Okay. Otherwise, you're going to have phase jumps in between inside this interference pattern. Okay, so that's this functionality here. This over here is if you have multiple cavities and you want to select one of them. We'll demonstrate that a little bit later, this capability. Okay, so we can press OK, and the next step we're just fitting to our to the virtual interference pattern. So we're trying to extract the envelope of this interference pattern. Okay, so we do that by using a fit. We fit to this interference pattern, and we extract the envelope. And the envelope of this pattern, okay, which is shown here, is equivalent to the first order interference pattern that would be produced in a dual traditional dual arm interferometer. And some examples would be the Michelson or the Mach-Zehnder interferometer. Okay, so it's exactly the same. The key here, what we want to do is we want to have the fit parameter, okay, as high as possible, because we can get good contrast between the peak and the valley. What we don't want to do is we don't want to go too far, because then we'll have more than one peak or valley for every real peak or valley, because there's noise on top of them. So we don't want to see the noise, because that's going to throw off the calculation for the center. Okay, so let's move this guy here. Now, in the next step, we're going to press OK, and it's going to automatically center the interference pattern, and it calculates the maximum and the minimum location of the so it started here. It was very fast, but it starts over here. The center starts over here, and it moves this way. Now, why did it stop here? Well, we need to have at least 2 peaks. Okay, we see 2 peaks here on both sides of the interference pattern to make the calculation. Because to locate the center, okay, how do we measure group delay? Well, we know the group delay that we're using, the virtual group delay, right? The virtual group delay is known, and we know that it's going to balance the real group delay, the group delay in the device, at a specific wavelength. So we know the group delay, and we just need to determine at what wavelength it balances the device. So how do we do that? We take this point, this point, this point, and this point, and we take the average, and it gives us the center of our interference pattern. We can't use just this point, because there's noise on the center, and that'll throw off the calculation. Okay. The other thing that we need these 2 points on both sides of the interference pattern for is to calculate the second order dispersion. So the separation between this peak and this peak, this peak and this peak, is used to calculate the second order dispersion. Okay, so let's go and look at the results. So actually, to sum it all up, the reason why see the bandwidth of the measurement. It's 1554.5 to 1555.1. Okay, and the bandwidth of the result is smaller, and the reason for that, okay, is that we need to have these 2 points. So it's going to go from the center here, okay, to if this interference pattern was moved to this side, it would probably be up to about 1555. Okay, so let's go look at the results, and yes, it is 1555 and 1554.7. So we have a good about 0.3 over 0.3 nanometers, 0.35-ish nanometers of bandwidth on our results, and we have about 0.5 nanometers of bandwidth on our measurement. Okay, so that's what we have here. Let's take a look at our GVD, and let's take a look at our dispersion length. Okay, so again, when measuring fiber Bragg gratings, you may ensure that the gain on the sensor is at 0 dB, and the output power of the laser is at least 1 dBm. Okay, so if you have any questions, please don't hesitate to contact us. We're always here to help. Um, and actually, what I'm going to do is I'm going to save this scan because it's and include it in the files that are available. So we'll save the scan as fiber Bragg grating measured using the Agilent 81600B option 160. Okay. And oh, the distance between, let's save that, the distance between the FCPC connector and the fiber Bragg grating in this experiment was about 25 centimeters. Okay. So again, if you have any questions, please don't hesitate to contact us. If you go to our website, it's www.inametrics.com. You go to the Contact Us page. There are several ways of getting in contact with us. Okay, so thank you for viewing the video, and we hope to hear from you soon.